At this time, well over 100 different elements have been discovered, either through direct observation or synthesis in a laboratory. And we probably don't want to have to memorize all the different properties of all of those 100 plus elements and their relationship to each other. So we have a tool which is the periodic table, and this summarizes that information in a very compact way. It lists all of the known elements. It does so by increasing atomic number. So start off, the first element is hydrogen, which has 1 proton, then helium, which has 2 protons, and you would continue going through the periodic table. This builds a series of rows, which are the periods of the periodic table. So there are 7 of those, and there are 18 groups, the columns of the periodic table going across. You will sometimes see these groups numbered from 1 to 18. This notation is a little bit different. So we have our A elements, which start on the left, and you skip over the middle and continue on the right. Go 1, 2, 3, 4, 5, 6, 7, 8. And in the middle, you have your B elements, which starts off at 2 and goes up to 11. Note that 8b actually refers to 3 different groups. This notation is a little bit better in my opinion because it conveys some useful information. Saying that you're in group 17, that 17 doesn't really tell you anything, but the number 7 does. We'll see why this number is useful later on as we start talking more in depth about quantum mechanics and how that affects the structure of the periodic table. Note that simply as a matter of convenience, we have taken one of the blocks, so it would be similar to, for example, this middle block here, but we've pulled it out of the periodic table and written it underneath. That's simply because otherwise our periodic table would be much wider and much less convenient to present in a standard piece of paper. But otherwise, our periodic table would be split right here, and this group would be shoved in, and our periodic table would stretch just a little bit further. Historically, there have been many efforts to group the elements together in a way that makes sense and is informative. One of the first efforts, which is reminiscent of our modern periodic table, was done in 1869 by Dmitri Mendeleev. Now, Mendeleev, he's an experimental guy. So there are about 50 elements, a little bit more, known at this time. And Mendeleev, he has practically a personal relationship with these elements. He knows what they taste like, what substances they form, how those substances smell. So he is very intimately acquainted with what to expect from these elements. So he does something a little bit differently than other people are doing. He groups elements with similar chemical behavior. Now, other people are arranging these elements in order of increasing atomic mass, and Dmitri Mendeleev does this as well, but sometimes because of those isotopes, you occasionally have one element which has less protons but heavier atomic mass. So someone else, in this case, would write those in order of increasing atomic mass. Mendeleev would flip them, and because he flips them, then he actually orders them by increasing atomic number, even though at this time nobody knows about the existence of protons. Something else he does is he leaves gaps for missing elements. So if there's an element that should have chemical behavior similar to the ones above it or below it, but there's not one discovered that fits that category, he assumes that there's something in between the neighboring elements that still needs to be found. What's really great about that is that he is then able to predict the existence of those missing elements, which is much more powerful than simply being able to list the elements which are known. One of the elements which Mendeleev predicted was germanium, which he called ecosilicon originally. Now, if we look over in group 4a of our periodic table, so beneath silicon and above tin is where germanium is. Now, when Mendeleev is constructing his list, no one has ever isolated or identified germanium, so there's no reason to even suspect that it exists, except there's something in this group of substances with similar chemical behavior which would fit between gallium and arsenic. So Mendeleev goes ahead and makes the assertion that, well, I think that there should be something there because I want to put arsenic in its own column where things have similar chemical behavior and gallium in the other column. I don't want to try and force them to sit here in the middle. So these are some of the predictions that Mendeleev makes for this missing element germanium. He predicts its atomic mass, 72 AMU, its density, 5.5 grams per centimeter cubed, that would have a high melting point and high boiling point. Its oxide would be something like white or gray. Let's see how well that he did in his predictions. Well, actually, we had an atomic mass of 72.3, density 5.47, same number by sig figs. Pretty good at a high melting point. We have 1,000 degrees is pretty high. Exactly the right boiling point, and the color of its oxide was as predicted. He made some other predictions too. This is just a summary of some of them. So you can see that without having ever done any experiments in germanium, that he was able to very accurately represent its properties. Now, this is the power of the periodic table. It arranges these elements in a way such that we can extract a great deal of information out of them based simply on where they are located. This is the periodic table as you've probably seen it. It shows all the elements which have been discovered so far. It's actually a little bit short. We've actually discovered up to 118 at this point, I believe. Up here, there's the atomic number, which is the number of protons. And then down beneath the elemental symbol, there is the atomic mass. That's in atomic mass units or grams per mole, either the way that you want to think of it. Now, we make some important distinctions in the groupings of the periodic table. We have what's called main group and transition group elements. So the transition group is right in here, and I include this section that we've pulled out of the periodic table, the lanthanides and actinides, in those transition elements. And then all the other elements in the left and the right blocks are our main group elements. And if our notation, those are the group A substances, and the transition elements are the group B substances. Now we can also think of the periodic table as being divided into some regions. We have metals, nonmetals, and metalloids. Metals are malleable. That means you can hit them with a hammer and just dent them instead of break them. They're ductile, so you can thread them out into wire. They're also very good at conducting heat and electricity. And they tend to lose their electrons, especially when forming compounds. With nonmetals, which are distinct from metals, they're brittle, they're poor conductors, and they tend to gain electrons instead of lose electrons. And then you have the metalloids, which are in between the metals and the nonmetals. And depending on the specific physical situation they're in, they might behave as one or the other. That's actually how computer chips work, because you can switch between the metal-like behavior or the non-metal-like behavior, the conducting or the non-conducting. So you can see that most of the elements are metals, all in the bottom left of the periodic table. And as we move towards the upper right, then here we have our group of nonmetals, and we have this band of kind of transitional metalloids in between. And sometimes people define these a little bit differently. Someone might call polonium a metalloid, others might call it a metal. And that's just because these are a little bit on the in-between side. We've seen how the elements in the periodic table, which are above and below each other in those groups, those columns, tend to have similar chemical properties. Now that's especially true for the main group elements. And in particular, we might single out in the very first column on the left side of the periodic table, group 1A, the alkali metals. So the elements in this group tend to be shiny, soft, very reactive. When they form compounds or are struck by ionizing radiation, they tend to lose a single electron to become +1 charged. right next to them, we have in group 2A the alkaline earth metals. These are somewhat similar. They're shiny, they're silvery white. They're not quite as reactive, but still fairly reactive. And they tend to lose 2 electrons to become +2 charged. Over on the far other side of the periodic table, one column before the column on the end, in group 7A, we have the halogens. So these are nonmetals, being on the other side of the periodic table. They're still very reactive, and instead of giving up electrons, they tend to gain electrons and become -1 charged. Now this gaining of electrons is intimately tied to their properties which make them nonmetals, and the property of giving up electrons is intimately tied to what makes things behave as metals. And we'll see why a little bit more once we start talking about the quantum mechanics of these elements. Now, the final group that we'll pick on is the one in the very end of the periodic table, group 8A. These elements are called the noble gases. So they're nonmetals and they're unreactive to the point that we can pretty much call them inert. They tend to not form any compounds at all and just exist as solitary atoms as gases. You might have noticed a pattern at this point. We said for our alkali metals that they would like to give up an electron and become +1 charged. Our alkaline earth metals next to them would like to give up 2 electrons and become +2 charged. Our halogens, we are on the other side, would like to gain 1 electron and become -1 charged. The connection between these is how far away they are from the last column of the periodic table, group 8A, our noble gases. What's happening is that the noble gases, they have a very favorable electron setup. That's part of why they don't want to react with anything, because they are already satisfied with their situation. These other elements in the periodic table, in order to obtain this noble status, can give up or gain electrons. So our halogens, they can pick up an electron and move 1 column to the right. Or our alkali metals, they can lose an electron and move 1 column to the left. And this kind of wraps around. So again, they have a structure now which is similar to a nobile gas. Now here in group 4A, we could either gain 4 electrons or we could lose 4 electrons. Either one would put us in this column here. So this gives us an indication of what ions we expect to be formed by the main group elements. Now this insight doesn't work quite as well for the transition elements, so we'll mostly use this for predicting ions formed by our main group elements. Now for these ions which give up their electrons and get a positive charge, we call those cations, those atoms which have lost electrons. Conversely, for our ions where we've gained electrons, these are called anions. Well, let's say that we want to predict what ions nitrogen and calcium are going to form. Well, looking at our periodic table, we find nitrogen over here in group 5A. So it's 1, 2, 3 to the left of neon, which means that it can pick up 1, 2, 3 electrons to get that preferred neon electron structure. So it picks up 3 electrons, that's going to give it a -3 charge. The way that we'll write that is using its elemental symbol N, 3-. Now let's look over for calcium. That's in group 2A of the periodic table. So it needs to lose 1, 2 electrons. And then it can look like argon over here. So calcium is going to form calcium 2+, having given up 2 negative charges.